There are likely countless times where someone who doesn't know the specifics about electrical circuits have used the terms power and energy in the wrong context. Despite how deeply linked they are to each other, they are different properties. Power is defined as the rate at which energy is delivered or work is done, or in other words, how quick energy is used up. Energy itself is described to be the capacity to do work, i.e., to perform actions. It is the thing that pushes electrons through an electrical circuit, thus creating current. To delve deeper, we must consider the unit we use for energy, known as the joule, which represents the work done when a force of 1 Newton moves an object 1 meter. This name came from James Prescott Joule, who was an English physician and established that all forms of energy are basically the same and can be changed one into another. Power also has a unit known as the watt and is a measure of joules per second. This means that power is the method we use to determine how much energy is being used over time. Now, the name watt comes from the Scottish inventor James Watt, who invented the double-acting engine, a development so defining that they named the unit after him. Specifically to the circuit, it is important to note that a voltage source is what produces energy. This means that energy and thus power are interlinked with the other circuit properties. Mathematically, we can look at it like so. What we know is that power is measured in watts, which are joules a second, or energy over time. Voltage is measured in volts, which are joules per coulomb, or energy over charge. Current is measured in amps, which are coulombs per second, or charge over time. And Ohm's law tells us that voltage is equal to current times resistance. Algebraically, we can rearrange the second equation to find that 1 joule is equal to a volt coulomb. Now, knowing this, we can sub this information into power to find that power is equal to VQ over T. But because current is in charge over time, that means the power is equal to voltage times the current. Because we know that V equals IR, we can also rearrange this equation to find that power is equal to both the voltage squared over the resistance and current squared times by the resistance. Many different ways to solve many different problems. Putting this into practice, we want to find the power over both resistors. The immediate thing we would do naturally is to use the voltage divider rule, Vrx equals Vs times Rx over the sum of the resistance, which gives us V1 equals 4 volts and V2 equals 10 volts. We can then sub this into the power formula, P equals V squared over R, to find that P1 equals 4 squared over 1 kilo, which equals 16 milliwatts, and P2 equals 4 squared over 2.5 kilo, which equals 40 milliwatts. But you might have noticed that the circuit is fully in series, meaning the current is equal across the whole circuit, so we could have used P equals VI to get the same values. Using the same logic, we could have skipped the voltage divider rule altogether and just used P equals I squared R, found the same thing. This shows that you only need so many known values to calculate the power over a certain part of the circuit.